4 minutes to start. You're right in here. Yeah. So you can use this through and spotlight if you want to. Okay. You're happy with it. All right. Yeah, that's fine enough. Yeah. Say whatever you want. Yeah. No, but oh yeah, sure. Well, unfortunately, yes, that's all right. Yes, according to the clock, we have 1 minute left. So we are slightly behind the schedule, and there will be the reception starting at 5 o'clock downstairs. So we will try to make it so that we will reach it roughly on time. Anyway, there will be something like 45 minutes for the talk. So I will be very brief in the introduction. And I will start it now because then we will save 1 minute for this. So it's really my great pleasure and honor to chair this final session for this noble lecture series, especially introducing you, Sir, now Fraser Stoddard. And Fraser actually asked me to be a little bit more unconventional in this and tell something how we get together. I met him 20 more years ago. We work in the same field, supramolecular chemistry. And then I actually hosted him 3 times in Finland. And each time he has had the different titles changing. And now, of course, it's one of the issues here that I will not go through his record. It's scientific, it's outstanding. He's one of the leading scientists in chemistry, that's for sure. And the principal idea is that, I think in late 70s or so, he discovered that there are weak interactions between molecules which can be used to create larger systems which then display functions. And of course, making interlocked molecules is not a very simple task, and you have to learn how the molecules self-assemble, self-organize, which kind of interactions are there. And with these words, I briefly ask Fraser to take the stand and tell us about the engines of the ages. Fraser.
Well, good afternoon, everyone, and I'm really the baby on the block here today because my good friend Barry has been wearing this medal for 2001. You do your calculations, 18 years or something, and if Ada is over here since 2009, 10 years, and I'm only 3 years in, so I'm really still practicing to see. Yeah. All right. Again. The other comment I want to make is to thank Carrie for his introduction. It's always been a very warm interaction that we've had. I visited you up in that northern part of Finland twice, and also Pekka for inviting me, and also finding out that we are fellow graduates of PhD graduates of Edinburgh University. So there's a lot in common here, yeah? Okay, so I'm going to talk about what's on the slide there, engines through the ages. Well, the wheel, of course, comes immediately to mind, and this one goes back many, many thousands of years. But I'm going to start more seriously with steam, electricity, or electrical motors, internal combustion, diesel engines, jet engines, rockets, and then we'll take a little look at what Ada was talking about, the field of biology, the motors there, and then these artificial ones, and who knows what's coming next. Always leave some space. Right, so if we look at trains, then here is one of James Watt, and he's another fellow Scot from the 1700s, steam engines. Here's one from more recent times, the northern part of Pennsylvania. This was used to pump oil out of the ground. And then quite soon afterwards, they started to find wheels. So if you go to the London Science Museum, here is the so-called Stephenson's rocket, which goes back to 1829. For many years, there's been this so-called Flying Scotsman that's made the journey between Edinburgh and London. This is the 1923 version. Here's one from Oregon that is used in a tourist capacity. And now we go to cars. But before we get there, we have to say something about electric engines or motors. This is one of the first that was put together by a Hungarian physicist, János Jedlik, and we'll come back to him later. Here's one that was gifted from James Joule to Lord Kelvin back in 1842. But notice the big gap, and I'll emphasize this later, it was more or less half a century before the first hair dryers and now, of course, cars come on the market. And in a country I visit many times, these trains that now connect about 60 cities the size of New York in China. High-speed.
The Beijing to Shanghai high-speed train has even clocked in speeds up to 480 kilometers an hour. That's about 300 miles an hour.
Incredible. Now the internal combustion engine. Here is an early patent drawing by von Langen, a German, that very quickly made it to action. I don't show that. I skip forward to perhaps one of the most famous of all times. This is the first Ford T, and it was sold by the Ford Motor Company in the US, 17 million of them roughly, through to 1917. And here is Fraser's Japanese car, the most recent Ford Corolla. And of course, linked to that is the fact that within 48 hours of hearing from Stockholm, I have my own place to park my Corolla. I learned something putting this story together, that diesel is actually called after a German engineer, Rudolf Diesel. And here is his first rendering of the diesel engine. Here is one of recent times that no doubt is made to make its way into some big cargo ship. Jet engines, we associate the name of Frank Whittle with them. And here we see taking off is a F-22. As that takes off, this is coming in from Perth in Australia and landing at London Heathrow back in March, about last year at this time. And that had flown 9,000 miles in 17 hours. Now here's something that really blows your mind. At any one time, there are all these contraptions in the air at once. And what it tallies up to is that there's 12,000 of them. And if we put roughly 200 to 300 people in them, there's 2.5 million, probably as much, if not more, than the population here of Helsinki, and half the population of the country are not on planet Earth on the ground here, they're up in the sky. Rocket engines, well, it hasn't such a good beginning because they were used during World War II by the German Air Force against the Allies, and particularly against London and Antwerp and places like that. But let's move on to 1969, when Apollo 11 took Buzz Aldrin and Neil Armstrong to the moon. And then I have a personal connection here to space exploration. This is Helen Sharman. She was Britain's first astronaut, and I was her tutor in organic chemistry at Sheffield University. So we're very often linked up through Twitter or something like that. But I would not have predicted that that's where she would have ended up. And she's an absolutely spectacular learner. She's a SpaceX rocket that's landing here. So now you can take off and you can also land. Biological motors, well, in the presence of ADA, there's not much I can add. I mean, here we see this interaction between actin and myosin, which gives us our muscle movement. And how it's happening, of course, is that this wonderful little rotary motor is taking adenosine diphosphate and phosphate and generating ATP, adenosine triphosphate. And all of us adults in this room are producing something like 40 to 50 kilograms of this chemical every day. It doesn't become an encumbrance because we're, of course, using it constantly. But if we are involved in strenuous effort, such as this is one of the Williams sisters.
She said 14 years after that first victory.
I'm promoting tennis. I also have to bring in the Scotsman. And
Andy Murray's having a lovely time now.
That's how the BBC.
He's there.
Now, back to reality. Bond, the word, means different things to different people. It's a noun, and we don't have a monopoly on it as chemists. Financiers use it, biologists use it, social scientists use it, anthropologists use it. And if we put the adjective mechanical in front of it, it's not exclusive to chemistry. It turns up in nature, art, architecture, everywhere. And of course in the cinema as well. And of course the first one is again an Edinburgh boy, Sean Connery. And when I was in LA, I was mistaken in the street twice for this. So what is the link to the world that I started out in, which was, as my Chairman Carey pointed out, supramolecular chemistry, complexes, and the one that I eventually went into? Well, this was what provided the basis. It was molecular recognition, self-assembly, and then ultimately template-directed synthesis that took us from this world of complexes into the world of interlocked rings, so-called catenanes, and this construct called a rotaxane. And I refer to both of these as mechanically interlocked molecules, or MIMs for short. So these MIMs, going back to the rotaxane, they derive these names from Latin, and Wikipedia get it right. They are molecules. They're the smallest representation of the compounds that are made up of these particular molecules. So the roadmap that I'm going to use, having quickly established, hopefully, a few introductory comments, I want to now establish molecular recognition a little bit more in the context that I'm talking about today, and that is the formation of, ultimately by templation, catenanes and rotaxanes, and then specifically look at molecular shuttles, molecular switches, then energy ratchets, and another form of templation that is relatively new in our lab, radical templation, molecular pumps, and then all of this takes us to the art of doing chemistry, not at equilibrium, but away from equilibrium. and there'll be a little bit of philosophy at the end. And so my life really changed, and some of you may have heard me be quite outspoken about my first 8 years at the University of Sheffield, when I escaped to Imperial Chemical Industries corporate lab. And it's a fairly long story, but eventually, in particular, this component of the wipeout weed killers that they were marketing all across the world to kill grasses and things like potato shaws, as we called them in Scotland. The very fast-acting, these herbicides, and didn't matter if it rained, which is important if you're in this part of the world, and inactivated as soon as they were in contact with soil. Okay, so how did we get there? In a sense, it goes back to Alfred Werner. He was a Nobel laureate in 1913 for his work on first sphere coordination between transition metals and organic ligands. And he had a disciple in the UK, Joe Chatt, and Joe Chatt had spent quite a bit of his career in ICI as well, and provided a huge amount of samples that I was able to fall or to come across at the corporate lab. Here's just a bit of comment about science from Joe Chatt. Scientific discovery is not yet predictable. It was the kind of thing we were talking about before lunch. If you have an exciting road to follow, do not be put off by those that say there's nothing at the end of it. They do not know. Persevere and enjoy the excitement of exploring the unknown. Anyway, I go to the corporate lab and I team up with a much younger Howard Colquhoun. He's now just retired from the University of Reading as a professor. And we worked very closely with a fantastic crystallographer, Carrie, that you hardly got to know because he only went to one conference in his whole life, I think, David Williams. And we published 250 papers together. I think that tells you how much close the collaboration was. And in illustration of my comments earlier today, it was not, as it were, orchestrated by any funding agency. Every one of these papers was scientifically driven by our interest in solving problems. And this was the student who carried, I think, most of them, well, not most of them, but 80 or so of the papers, Sandra. All right, and so we entered the whole area of so-called second sphere coordination. In 1981, we had noted that this platinum complex, it's dicationic, and it has a bipyridinium unit that is here, and amine ligands, and this particular crown ether, and these are macrocycles thanks to Charles Pedersen, who was one of the 1987 Nobel laureates. They came out of the blue from DuPont. This was a big, big change in macrocyclic chemistry. Just curls its way around in a horseshoe-like manner around this transition metal complex. And, well, you couldn't be at ICI and not then think this other one of the herbicides dicot would be perhaps complexed as well. All you had to do was take away the metal and rely on the acidity of the bridging methylenes up there. And this worked, of course, and we had very good, strong complexes between dicot and dibenzo-30-10. What took a little bit longer to solve, and we just over-designed for a while, was to find something to bind paraquat, or methyl-viologen. And it was really very simple. All we had to do was move the polyether loops around the benzene ring from being ortho to each other in the dibenzo compound to being para in this one. And we made this compound. Cram had made it for other reasons back in the 1970s, and lo and behold, it formed strong complexes with paraquat. That got us to a point where we could put blue inside red, and before we could therefore make mechanically interlocked systems, we had to come up with some sort of blue ring, and ultimately we did. This became known as our little blue box, and this is a haven for pi-electron-rich aromatic systems, putting red inside blue. So just in summary, this is the electron-poor component that came out of ICI, and this is a rather inexpensive expression of an electron-rich one, this 1,5-dimethoxynaphthalene. And so let me just define the icons that I'm going to be using. I use the lock and key principle of Fisher, or metaphor of Fisher. When the key is out the lock, molecular recognition is off. When it's in, obviously it's on. This is how we used to draw 5, 6, 7, 8-membered rings. This is the icon for templation. If we have radical recognition, we go from red and blue to purple. Sometimes, of course, we'll need to use a little bit of heat or electricity. Sometimes, if we're looking at switches, the ratios will not be 1-to-1, and sometimes to drive switches and ultimately maybe machines, we're going to have to use some chemicals. And so I have some movies to just go over what I've already said, and this is just showing how we put paraquat inside BPB 34-10. That was back in 85. In 88, we had turned it around to put red inside blue, and we had made the little blue box. And you will see we're really talking about a cubic nanometer, so we're down in a very, very small level, the lowest in the sort of nanometer scale before you bridge down into angstroms. In order to make this little blue box, because it's pretty highly strained, it's really a cyclobutane ring with these aromatic units in its sides, we had to use a template, and this is the template, and we had to remove it afterwards. All right, so that's establishing the molecular recognition. The templation could then be used to form catenanes and retaxanes. And so this was really the big breakthrough experiment back in 1989. Here is the dicationic species that was used along with xylene dibromide in the presence of free equivalents of the template. And what happened was that they didn't talk to each other. There was no evidence of any complexation. And this makes it, I think, really interesting because we form a carbon-nitrogen bond. And, you know, Barry told us right at the beginning that, you know, he loves forming bonds. And he was down on his knees praying for these bonds to form. We didn't have to do this because it happened just at room temperature in acetonitrile. And when this happens, you make a dication here, a bipyridinium one, and like paraquat, it wants to go inside. So it worms its way inside, and these vertical lines show that we have switched on CHO and donor-acceptor interactions, and also weak CH-pi interactions. So it's actually DNA-like in this direction, and proteinaceous-like in this direction. And after that, it's all the way downhill because another carbon-nitrogen bond forms, and we've got the 2-catenane. So this is actually not at all planned research. This is just presented to us on a plate. I think it's a very elegant synthesis, if I might say so, insofar as you make a covalent bond, you switch on non-covalent bonding. Here, you make another covalent bond, you switch on even more non-covalent bonding, and lo and behold, you have a mechanically interlocked molecule. And what was really stunning for us was it was a 70% yield. In the hands of David Williams, we got the crystal structure in next to no time. And so on the image you see here, up in the northeast, down to the southwest, we got acceptor, donor at 3.5 angstroms from each other, with the CH-pi interaction in here. So DNA-like in this direction, proteinaceous-like in that direction. And here's just a movie showing that once you have this as a dication, it sucks on the ring, and then the last bromide is kicked out here, and we have the mechanically interlocked molecule. As I say, it's going to be around about a cubic nanometer. And excitement grew because we found out, principally using proton NMR spectroscopy at different temperatures, that there were 3 processes. There was this very fast one with a barrier of about 9 kilocalories per mole at room temperature, happening a couple of million times a second. And then the next one, which was around about 12.5 kilocalories per mole barrier, was a pirouetting motion as this red ring goes round the blue one. We've no control over whether it's clockwise or anti-clockwise. And then finally, the one that rips all the, or most of the non-covalent interactions between red and blue apart is circumrotation, about 16 kilocalories per mole, or about 30 times a second. And I won't talk about it today, but this was the process that we used over a decade in collaboration with Jim Heath in putting together molecular electronic crossbar devices. Let me go back to the synthesis again, and I'll go quite quickly now because the template is no longer a ring. It is this dumbbell, and I draw it like this, but of course it's flying all over the place, and you won't expect it to be as efficient as was the synthesis of the catenane, but nonetheless, it turned out that it was about 32% yield. And that gave us our first rataxane, in which we had 2 sites. And here the movie just to show you what's happening. So we got the same interaction that we had in the catenane, and then the formation of the mechanical bond. Now, we can draw this differently, and this is where we called it a molecular shuttle, very simply because this is a system that is degenerate. It reads the same from left to right, depending on where the so-called cyclophane is sitting, and it's jumping back and forth, indicated by dynamic NMR, about 2,000 times a second. This is a barrier of 13 kilocalories per mole. So here's the movie, just showing that. And of course, this is much idealized. I mean, these molecules are really wound up quite a lot. A little bit of advice for people publishing. It often comes up. How do you get past the reviewers? Well, the Jack's article was a communication. We had 4 sentences as a conclusion, and the then editor of Jack's asked us to take them all out. This was hype. Now, fortunately, I stood my ground, because here is the first time that I actually mentioned molecular machines. Insofar as it becomes possible to control the movement of one molecular component with respect to the other in a 2-rataxane, the technology for building molecular machines will emerge. Right, and to take that further, by 94, what we had done was to remove the hydroquinone rings and put in benzidine and biphenol. And as we predicted, the benzidine is a more pi-electron rich unit here, and so forms a stronger interaction with the blue box, and we end up with an 84:16 ratio of these two. And here, again, this movie shows that the blue box will spend more time on the green component, 4:1. That same system we could address electrochemically, but here I show just using acid. We can protonate these nitrogens, and we can then just use Coulomb's law, if you like, straightforward repulsion between the 4 positive charges on the box here and the 2 on the now protonated benzidine unit. And that sends the ring right over onto the biphenol unit. And of course, if we add base, we can reverse it. So that was the first of our molecular switches in 1994. All right, so to go on from there, the grand challenge is how do you get to machines? Well, let's just make a contrast with the macroscopic world. Here is a rendering of I guess, sculpture by a Dutch artist. It's made of wood with sails, and these are the flat sands somewhere in the Netherlands or Holland. And what's driving this along, of course, is the wind, and what's important here is things like inertia, momentum, friction, gravity, and so forth. If we're in the world that we heard about from Ada, then we are looking at a fairly different situation at the micrometer level, where there are constant movements. Brownian motion is very important, thermal fluctuations, And it's really the viscous forces of the liquid in the cell that dampens the movement. And physicist Dean Estumian up at the University of Maine has referred to this whole activity by these biological motors as swimming in molasses and walking in a hurricane. And the same principles need to be used in the design of artificial molecular machines as for the biological motors. So if we go to the mechanical world, which would be that sculpture moving across the sands, or maybe even better, we want to have, say, a bicycle go over a mountain into a valley and then over another mountain into this valley. Nothing changes in terms of the valley and the mountain. I don't know why this one has gone. Well, we still have one. It's beyond my technical ability. Maybe it'll come back. Anyway, so this is a top-down manner. These are macroscopic machines. This is more likely to happen by a very different approach. And it's a juggling of energy wells, raising them and lowering the transition states and going through this juggling act to get, I'll now call this, a collection of molecules from the starting point up to the end point here. And so we have to take this into account and design things called energy ratchets. And now what you see here is a dumbbell which has been designed so that these so-called end groups are not actually stoppers. They've been finely experimented on until we have something that is neutral at one end and charged at the other end. And they're just of a size that is sufficient for the ring to get on, to stay on until we change some of the properties. And so, as you see it drawn here, this ring comes over the neutral end, so that's over this hump here. And we have this complex, I'll just call it a one-to-one complex, for that's what it is. And then we reduce the positive charge by taking these bipyridinium units to radical cations. So we go down for 5 charges overall to 3. The ring also changes its size to some extent, we believe, and it leaves by the charged unit here. So this ring is constantly coming on and going off. Now, this is not a molecular machine because we take a ring out of solution and we put it back in again. On this energy profile, what you can see is the rings would come over the lower transition state, go into the well here, so that's this particular species, and then when we do the reduction, we destroy the molecular recognition and they're obliged to leave by the right-hand side. So that's what's often referred to as a flashing energy ratchet, and here is the movie that supports this feature. And you see the reduction, it comes off there, and when it's in an oxidized state, it comes on over the green unit. Now, I mentioned reduction. The person in 2010, when we had moved from UCLA to Northwestern, that really came up with a transformative piece of research. And again, this illustrates, I think, much that we were talking about in the morning. He had enough freedom, he felt, just to play around. And what Ali Trebosi did, I should mention that he's now at, somewhere it should tell you, New York University, Abu Dhabi. I don't see it, but here we are, in the United Arab Emirates. Obviously as a, now I think, full professor. And so he carried out an experiment that could have been carried out any time between, say, 1988 and 2010. So it was a long period of time. Nobody had thought that it would be conceivable to do anything that would put paraquat, or methyl viologen as it's often called, inside the little blue box. We got 6 positive charges, but what Ali argued was, what would happen if they were all reduced to radical cations? So he takes some zinc cast. He makes his own little glove box with some cling film. is a nitrogen atmosphere. Of course, this is very important. And lo and behold, he gets a one-to-one complex. And it's a strong complex. It is round about this value here in terms of its Ka value. And it's mainly enthalpically driven against, of course, a big loss in entropy. And he's joined by graduate student Albert Fahrenbach, and they come up with the crystal structure and find that the paraquat radical cation is almost sitting orthogonal. It hasn't much choice sterically inside the reduced little blue box. And what's more, in the crystal, these all stack up because the radicals are talking to each other over an infinite stack in the crystal. And so, as to summarize, this was a breakthrough by one of the postdocs in 2010, and that has fed through to a whole series of people. I think there are around about 13 here who have just done their own thing in coming to my group since then. The radical school that was founded by Ali. So introducing radicals into the scene gave us this ability to form complexes of over 6 kilocalories per mole of energy, that is stabilization, provided we had this tris radical trication. On the other hand, if we were to oxidize it, the bits would fly apart, thanks to the physics again of interactions between these positive charges. And so this is actually no more than a thought experiment. This is just taking the dumbbell we had before and putting the charged pyridinium unit on the left and the neutral one on the right. And we could now surmise that if we reduced, the ring would come on from the left-hand side, sit here, this is the strong one-to-one complex, and then when we oxidize, it would depart from the right-hand side. And so that was used to design a molecular pump, and I'll define it chemically in a minute, but basically we have a pseudo-stopper here over which the ring will come only when we've reduced the system, and this is a radical cation, and these are both radical cations. And then when it's on here, as this movie shows, once we oxidize, the ring will move away because of coulombic repulsion to what we call the speed bump, this green component here. And you will see on the movie here, it'll, I guess, be really something that Barry will enjoy. That, of course, is a triazole ring, and we used this wonderful click chemistry to put the compound, the dumbbell, together in the last step of the reaction. A subtlety that I just want you to see here is as the second ring comes on, the first one wants to come back to here. And this speed bump is designed so that that first ring, which gets over here, let's just watch it, right? It's fully oxidized, but once it's reduced, it wants to come back, but it can't. And this one comes and joins it. All right. Here's another movie just showing this principle. And this is it laid out in details. We do the reduction, we bring the ring on here, and then we oxidize, and we need some heat to get it over that hump onto the collecting chain, and we can repeat this whole process and bring two on. And we're actually now looking at a molecular machine that we call a molecular pump, and we're doing chemistry away from equilibrium. So here's the chemical constitution, and I have to get over the point here that there were probably 30 or 40 variants of this dumbbell made until we got the one that really works well. It works, as shown by this NMR experiment, at 42 degrees centigrade, so it's a little warmer than it is here in Helsinki at the moment. And we use zinc dust and nitrosyl hexafluorophosphate as the reductant and the oxidant respectively to get us to this stage where the ring is sitting there, and these chemical shifts can be interpreted as sitting there. And with a careful eye here, you can see the growth in these signals in the high field region, which is when the ring has crossed over the speed bump and is collected on the polymethylene chain. And as I said, we can repeat this again. And it takes an hour and a half at 42 degrees to get these rings across. So this is quite a slow situation. Here's just a movie that is capturing what I've been telling you with all these changes in colors. And so there's the first ring going over the speed bump, taking an hour and a half for all of them to get over. Here is the reduction bringing the next one on. This one was wanting to come back, but the speed bump stopped it, and the second ring goes and joins it. All right, so to summarize, we're doing chemistry away from equilibrium. We're bringing on one ring, and if you look at the physical chemistry of it, the barrier to the crossing here is 23 kilocalories per mole. We just measure this from the kinetics. And the really wonderful thing is the second ring with an experimental is coming on over the same barrier. So the message there is the presence of the first ring does not stop the second one coming on with the same ease. This is where we didn't go, just bringing on more and more rings. So this is just a movie. We have one ring on, and each time you see the energy ratchet being used here, here's the third one coming on, and it's a repetition of reduction, like this, to bring it on, and then oxidation and thermal energy to push it across. And what was happening here is that energy level was moving up, and that's meant to indicate that each cycle traps one ring in an even higher energy state. And, of course, some of the energy will be going to heat, as always, but some is trapped, and so work is done. And I won't have time to go into it, but from a materials point of view, we produce both enthalpically and entropically dominated polyretaxanes. Now, there was a redesign by a very brilliant Italian postdoc that came and joined the group. He removed one of the methylene groups between the pyridinium unit here and the speed bump. And his argument was that this would bring the positive charge closer and would push the ring over more efficiently. And he also, for various reasons, moved the methyl groups from their original positions to these positions 2 and 6. And this was repeated, and what he did was an experiment at room temperature by NMR. It took the same length of time, but if you extrapolate up to the 42 degrees, then this pumping could be done in literally minutes now. The next thing that Christian Pizzato did was to say, well, it's wasteful, of course, to be always adding chemicals and so on and so forth. You're just producing waste products. Could we do it electrochemically? And so he built his own electrochemical cell and went on to show that this was possible. And in so doing, he decided to move to a dual pump. So here we have a pump at each end of this molecule, and in the middle, it turns out there are a total of 36 methylene groups interrupted symmetrically by 2 ammonium sites here, so it's positively charged. This is not a place where the rings with their positive charge would like to go. Here's the very fine NMR spectrum of the dumbbell, or whatever you want to call it here. You call it a dual pump, DP1 8+. And here is the experiments that he did, namely to, oh dear. Okay, right. We're back again here. No, okay. This is the oxidation that, sorry, I'm getting shown by these flicking slides. This is a reduction at 700 millivolts, the purple here, and then give it time to rest for 20 minutes and then oxidize at 1.4 volts. And this brings on rings from each end of this, this dumbbell component, the dual pump. And it very cleanly and in good yield, 85%, produces this free retaxane. So we have the dumbbell plus 2 rings. And this can be repeated and brings on another 2 rings, and we have a 5 retaxane. Again, well characterized. And at the moment, what we're looking at is a longer polymer. This is a ethylene glycol chain with a number average molecular weight of around 2,000 with about 50 repeating units of OCH2CH2. And again, you'll see, of course, just for Barry's sake, there's been 2 clicks here. Yeah? Not just 1, but 2. Amazing. Yeah. And it works like no one's business. Thank you, Barry. So this gives us dual pump number 2. And now what we do is go through the same cycle as I've expressed before and get a 3 rotaxane. And we can go from there to, let's see, a 5 rotaxane. And all of this can be done in one pot without any isolation of the products. This is, what are we doing here? Dual pump. Seems to be the same thing again. Sorry, these slides have maybe got messed up. Anyway, we can go from 3 to 5 to 7. So that's 2 rings, 4 rings, 6 rings, 8 rings, 10 rings, 12 rings. And that is where it has been taken without any isolation. It's just repeating the addition of, this time, cobaltocene as the reducing agent and nitrosyl hexafluorophosphate as the oxidizing agent. And in between, there's always this heating step to encourage the rings to go on to the chain. This has now been repeated electrochemically, so we're up to a 4 rotaxane or maybe beyond that. So that's what's ongoing in the lab at the moment, that we can, by electricity, power the production of these polyrotaxanes. So, in summary, what are these radical cations good for? They're good for establishing strong and directional homophilic recognition. It took us a quarter of a century to get there, but we finally got there. Producing, therefore, strong supramolecular complexes, over 6 kilocalories per mole of binding energy. It allowed us then to template the synthesis of mechanically interlocked molecules, like bringing the 2 blue boxes together. It ends up being an octacation. Who would have thought that that would have ever been possible? But using the radical chemistry, we can do it. Obtaining air-stable, persistent organic radicals. So when we had this homocatenane, when we brought it out of the glove box, it went up to 7 positive charges and 1 radical. And so we have this sort of rare example of a persistent organic radical. It's a good way of piling on many, many positive charges. I think we're up to 24 in a very, very small molecule. So that the mechanically interlocked molecules, when they're fully oxidized, are full of coulombic repulsions. And who knows what these new materials might be useful for. And in a polymer sense, we can bring about large expansions and contractions just by using the radical chemistry to have the polymer contracted and then the coulombic repulsion to have it expanded. And as you've seen, I've illustrated it with the synthesis of these molecular pumps. And this is a dream. A one-step synthesis of a polycatenane. This is like Auris sitting over here, and she had a very nice necklace this morning with nothing but rings on it. There it is, see? And that's what we want to be able to make in one fell swoop. So here's just a movie showing these coming on, and in the interest of time, I'm going to switch to a piece of music. Now, this is going to last about 4 minutes. Is that all right?
Totally fine.
Yeah. And I have a little bit more after that. How many more minutes have I after?
After that, 2 minutes.
Oh, my goodness. So, yes, I have no regrets. That was a 35-year odyssey. A lot happened that was different in between it, and I have a lot more slides. But look, I think the get-together party's more important, and maybe somebody has a question that they want to ask. So I'm actually going to stop there and thank everybody for the warmth of the hospitality that again, I am experienced here in Finland. You have a wonderful country. You have earned, as has been pointed out already, the status of being one of the happiest places in the world to live. Shortly, I think Scotland may well join you in that and give you a run for your money. Same sort of size of country, but that's up to the people that are throwing a tantrum down in the bigger country to the south. And on that political note, I will end and say thank you.
Thank you. One question.
Sure,
so
sure.
Do I really need this? So, now there's a chance to ask one question before we go.
Barry, okay.
You need this.
Are these comments? Did you ever test them for LD50 in mice? And the second question is related. Did you ever taste them? What do they taste like?
Oh, see, no. Well, we'll go backwards.
I would taste them after you test them.
Wait. These are poisons, if you like, potentially, because of they're weed killers, yeah? So they wouldn't be...
Yeah, but they got all these extra features.
Yeah, they have.
They can become antibiotics.
Yeah. Well, I haven't summoned up the courage to taste them. But if you want to, Barry, we'll supply you with... Yeah. And no, we haven't shown them to mice either. But
is easy, but these you can't smell, right?
No. Yeah, so I think you illustrate the fact that there's a whole lot of, and the one thing I would...
Radicals are cool, I like that.
You like...
They can't tolerate any oxygen in there.
No.
Well, azide loves to go to a radical.
Yeah.
And it even dimerizes to make 6, and then it even goes again, and then it goes to nitrogen. The barrier is very low.
Yeah. Radicals I have fallen in love with. Absolutely wonderful things, and it took me most of my chemical career to get there. I was a slow learner compared to you. And radicals are wonderful. Yeah, thank you.
So thank you. I think it was really very good question to end the
absolutely.
Seminar what we have.
You wouldn't expect it to be anything other, yeah.
Thank you.
Thank you.
Thank you, Fraser. Thank you, Ada. Thank you, Barry. It's been a fantastic afternoon. And now I will just tell everyone we should go to the plaza area, and there will be some servings. And we will also give some prizes. There are several prizes to be given out, and it's fully in Finnish, so you can just relax and talk with the people, but you should probably join us there too. Okay, thank you very much, and let's clap one more time.